Standard integrals. So now we're going to add to the list of the ones that we've done already. Number one is the one that we've done the most of. That's standard integral, which is the power rule. Add 1 to the exponent and then divide by that number. And then I snuck in a natural log one on you. Was that yesterday? Just to show you that working backwards is hard to do sometimes, and it's hard to recognize those things. So anytime you have a 1 over x, you're going to be very tempted to use number 1 here. Add 1 to the exponent and divide. But that's why we have here in number 1, this works unless n is equal to -1. Because if n is equal to -1, you have option number 2 instead of option number 1. And to recognize that all 1 over x functions are, the integral of them will be the natural log. We also have e to the x graphs. Now, the derivative of e to the x is e to the x. So integration is pretty easy as well. The integral of e to the x is e to the x. So I added in this one something that we're going to look at more today, is what happens if you have an extra constant inside. Well, if you had e to the 2x and you did the derivative, what would happen? If I had y equals e to the 2x, if I did the derivative, well, I would get e to the 2x again, but then I'd have a chain rule, and I'd have to multiply by 2. So if you were working backwards, and you started with the derivative being e to the 2x, and you worked backwards, well, you would also still have e to the 2x, but since this e to the 2x has a chain rule where you'd multiply by 2, working backwards, you'd have to divide by 2 to compensate for that. And so that's why we have a 1 over k, or divide by k, the whole thing, to begin with, if you have that extra constant. And that's one of the key things that we're going to be looking at today. So here we have the integral of 12 over x. We have a single x on the bottom. Perhaps we want to use the property where you can bring out a constant in front, so it's really obvious that you have a 1 over x. And the integral of 1 over x is the natural log of x plus c. Here's an example with an e to the x function. Of course, it doesn't change, but because of that 5 would have a chain rule where you would multiply by 5. When integrating, you'd have to divide by 5, and then plus c. And of course, we've learned if you're adding or subtracting a bunch of integrals, a bunch of functions inside of an integral, you can just take the integral of each one separately. So how do we do the integral of 7x? Well, that's the first one. Add 1 to the exponent, divide by the exponent. Minus, there's a 1 over x graph. That's going to be 3 natural log of x. Plus e, nothing's going to change, but we would have, since we're multiplying by 1/3 in there, we'd have to divide by 1/3 to compensate for the chain rule. Plus c. Of course, this term right there is a complex fraction, so we're going to have to turn this into, just rewrite the rest of it. But dividing by a fraction is like multiplying by the reciprocal. So if you multiply by 3 over 1, you'll get 15 e to the x divided by 3 plus c. And then 2 other integrals that come up, and again, in these examples, I've added that extra variable or extra constant inside. I'll highlight that again in green for you. So we could take this out and I could do one just separately with just sine of x. And this is where I think sometimes things get confusing, because the derivative of sine was cos, the derivative of cos was negative sine, so one of them's positive, one of them's negative, and then when you work backwards, everything's backwards again. Now the integral of cos is positive sine, where the derivative of cos was negative sine, and the integral of sine is now negative cos. So you can see just the fact that we're adding more of the same but different is going to confuse you, and it's going to be easy to make a mistake. So what do I always do for myself is I just remember one direction, just the derivative. Because if you know the derivative and you can write out the derivative, you can see how it's going to work backwards. And the way that I always remember now which one's positive, which one's negative, is I think of it graphically. So that's the graph of sine. If we think of our tangents starting right at 0, our tangent slopes are going to start positive. So that means that the derivative of sine is equal to positive cos. Similarly, if you want to think of the graphs of cos as well, same thing happens. Here's my graph of cos. My first derivative is 0, and then after that, my slopes go negative. So that means that the derivative of cos is negative sine. If you think that way, okay, this is moving forward. Derivative of sine is positive cos, so moving backwards, the derivative of cos is the integral of cos is positive sine. Notice that we have that right here. The integral of cos gave us a positive sine. With cos, the derivative of cos is negative sine, so working backwards, that negative you'd have to move to the other side. The integral of sine will be negative cos. And so that's why we have a negative right there. And I find if you remember just the derivatives and write them out, you'll be able to see what you need to go when you work backwards. Of course, if I had cos of, if I had the integral of sine of 3x, well, when you're doing a derivative and you have a 3x inside, you have a chain rule. So you'd multiply by 3. So if you're integrating and there's a 3x inside or a 5x or anything, the opposite, to compensate for that chain rule, you're going to have to divide. So that's why there's this division in these ones. So regular integration, if you just had to integrate just cos x, easy, it's going to be sine x plus c. But if you have that extra number inside, like we do in this first example, find the indefinite integral of sine of 5x. So if I have sine of 5x, and I'm working backwards, this is where, having thought about my derivatives, going backwards from sine is going to be a negative cos graph. So we'd have a negative cos 5x. Now if I did the derivative of that, I'd have a chain rule which multiplied by 5. So to compensate, I have to divide by 5 plus c. One more example in this section. A bunch of them combined. So if we're going to integrate this with respect to x, we're going to get the integral of x squared plus e to the x minus cos of x divided by 3 dx is going to equal, first one is just an add 1 to the exponent and divide by that new exponent. E to the x is just e to the x. No extra number inside that we have to worry about a chain rule. And then the derivative, the integral of cos. Again, you might have to think, where's my cos? Cos integrates to sine. The signs don't change. So this will still be negative sine x divided by 3. And because we have a 1/3 in there, we have to compensate with a 1/3 plus c. So our final answer, just to write it without that complex fraction,